Okay, so more about special relativity. First off, it's been a little while since I've done this, but it is what it is. I'm posting them now. Obviously, if you're watching this like a year from now, you're not really going to notice. You're just going to be going through the playlist, so that's good. But yeah, I'm going to try to ramp this up because I haven't actually taken this class before. I've just studied it on my own, and I got accepted into the school I really want to go to, which means I'm going to start studying it even more now because I want to do really, really well. So we're going to talk more about relativistic. Well, we haven't talked about relativistic dynamics. We're going to talk about relativistic momentum right now. So I want you to consider two scenarios. I have these two charts. The first one is a mass. I should make a note. It's not apparently clear. I'm separating the before the collision and after the collision. So if we look on the left here, we have a mass 2m at rest and another mass moving at a velocity of minus 0.750 c. We have this collision, and I'll draw a little arrow here. This is a clear momentum problem that we learned in Physics 1. So first, if we look at this situation, let's analyze the momentum. So momentum initial, we're using the prime notation, is just m1 v1 prime initial plus m2 v2 prime initial, which the first one is not moving, so this is just 0. And then here we just have minus 0.750 cm. So the speed and the mass. Now, hopefully, so just remember, if you forgot, momentum is mass times velocity. Momentum and velocity are vectors. So we want to break that up in components if we ever have to. So that's important to know. I'll have a series on momentum coming up soon in my Physics 1 playlist, so that's an option too. So hopefully, we want conservation of momentum. Momentum initial equals momentum final. That's what we want to see happens. We want momentum to be conserved. So look at momentum prime. We're using the prime notation, final. That's m1 v1 final plus m2 v2 final. Okay, so what do we get? Well, we have 2m times the final velocity minus 0.500 c plus just the mass times 0.250 c. And you'll get momentum final equals momentum initial. So that's the first thing that we wanted to see, is that momentum's conserved. But if we look here at the second one, now it's a little different because we have a moving reference frame moving at very fast speeds. Now, I don't want to go through this all again, but you'll find out if you do the momentum initial, it does not equal momentum final. And this is a problem because conservation of momentum should be valid. So as you could probably guess, we need some sort of factor to fix this. One that in low speeds simplifies to the classical sense, but works for relativistic senses. So I'm just going to give it to you down here. Momentum is equal to mass times velocity divided by the square root of 1 minus v squared over c squared. I'm going to box this. That is relativistic momentum. And of course, you could break this up and say momentum in the x You could say momentum in the y. I'm going to keep them off for now, but you can break this up into its components just like we're used to. Now, if you were to look at momentum initial prime now and put that in, so that would be m1 v1 initial over square root 1 minus v squared over c squared plus m2 v2 prime initial over 1 minus v squared over c squared. If you were to plug these in, we have the speeds and we have all that. You should get minus 1.134 mc. And if you do momentum final, again, if you were to plug the final momentum in, I'm not going to, but if you did, you should get the exact same thing. In other words, it should show that momentum is conserved. That's good. But the real big thing here is if we look at in the moving reference frame, again, I'm not going to plug them in, but it's the same idea. You'll get 0.956 mc, 0.956 mc. So you get momentum is conserved. Conserved. That's key. Now, if we were to just take a quick example, let's say we want to find the momentum of a photon. Let me turn my light on. Moving at a speed v equals 0.86c, so 86% the speed of light. We want to know the momentum of this photon. Well, let's use our new fancy definition of momentum. Really cool looking formula. So you would have to be given the mass of the photon, obviously. We know the speed, we know this. So momentum is going to be equal to, the mass is about 1.67 times 10 to the negative 27th kilograms times 0.86 times 3.00 times 10 to the 8th meters per second, all over the square root of 1 minus 0.86 squared. If you plugged all this in, then you'll get your momentum is equal to 8.44 times 10 to the negative 19, really small number, kilograms times meters per second. Now, another way to look at this, which is how we normally will with these sort of problems, is let's take what we had originally. Momentum is mv over the square root of 1 minus v squared over c squared. Another way to do this, let's multiply both sides by c. Then pc equals mvc over the square root of 1 minus v squared over c squared. So I just multiplied both sides by c. Now I'm going to say pc equals m c squared times v over c, all over the square root of 1 minus v squared over c squared. So it's still the same. If you were to simplify this and this would drop, and you'd be left with CV. So it's the same thing. It just looks a little different. Now, if you plug all this in, you'll get a different unit. So if you plug in our values, electron volts. I'll go ahead and box this. I'm sorry, divide by C. There we go. That's why there's a C here, is because you divide by C. So this is used a lot we'll talk about something called rest energy. That's actually the next bit. We're going to talk about relativistic energy, hopefully tomorrow. Rest energy, you'll see MC squared very often, which is pretty famous. Obviously, maybe one of the most famous ever. So next video, we're going to talk about relativistic energy. And then after that, we're going to do probably some practice problems and go through it. So